Hi, I'm Deborah Byrd, and you're watching EarthSky's Sun News of the Week. C. Alex Young, our heliophysicist friend from NASA Goddard Spaceflight Center, is here with me today. Hello, Alex.
Hello, how are you?
I am just very well. Let's talk about this. Can
Yeah,
you
it's
see this picture? Yeah.
pretty exciting. We were wondering if that was going to be headed towards us, but even though it turns out that that was a backsided event, it was strong enough that it sent protons, high energy particles heading our way, which you can see as the snow on the images.
Right. So what was this? This was just this big thing that's blasting off the sun here. That's
Yes,
just a coronal mass ejection, right?
yes, that's a coronal mass ejection. It more than likely came from one of the regions that just rotated out of view. I believe it's AR 3889. And it looks like that was a filament associated with the active region, given the size and the material, and it was strong enough that it actually created a blast wave, what we call a coronal wave, that spread all the way around the sun. We could see it on this side, on the Earth facing side, but it also sent particles, even from the backside. It sent solar energetic particles our way.
Okay, so this when you can't see it so much on this red part of the image, but on oh, now you see it. Like on the blue image, you can see all those little that what looks like snow on the image.
Right,
And
right,
that's the solar radiation storm striking
right.
this
Those are
spacecraft.
Right. Those are high energy particles, mostly protons, that are traveling near the speed of light, that are hitting the camera, hitting the electronics, the CCD on the camera, causing those streaks and that snow pattern.
And is this the SOHO spacecraft?
Yes, this is the SOHO spacecraft. These are two of the instruments called LASCO C2, which is the red one, and C3, which is the blue one. These are coronagraphs, which are basically artificial eclipses that we've made by covering the telescope, covering the disk of the sun, so that we can see this very faint structures coming away from the sun.
And so that's that disk that you see in the center of this image is just there to, mask the sun's brightness.
Exactly, because what you're looking at here is visible light. So this is the kind of light that we see with our own eyes. And in that kind of light, the sun is incredibly bright. That's,
Right.
when we go outside, that's basically the sun that we would see if we could safely look at it. But you can't. You have to block out that bright sun, and that's what we're doing here. You see the white rings. That's actually where the sun is. The disk itself that blocks it out, you have to actually cover more of it because we can't make an eclipse as well as nature can during a regular total solar eclipse.
Oh, so this is visible light, did you
Hmm.
say? And
Yes,
so
ma'am.
if we were watching a total eclipse of the sun and one of these coronal mass ejections happened, would we see it looking like this?
Well, we wouldn't see it quite like this because this is much more time than we would see during, during a
Oh,
total
okay.
eclipse, you could only see up to about 7 minutes.
Oh, so this is
Um,
not in real time. This is sped up.
Right. This is sped up. Each one of those frames is somewhere around 12 to 20 minutes apart. However, we have recorded, a CME, like a still shot of a CME in total solar eclipses. As a matter of fact, I think in the one that occurred in April 2023, we did, and the one that occurred in December 2020, uh, people took images from the ground and actually captured a coronal mass ejection. Though they just saw one frame basically of what you see here.
Oh, I don't think I've been aware of that. You'll have to send those images to me, Alex. I'd like to see those.
Sure.
We'll put them up somewhere so that people can see them. That's so cool. So this was like a coronal mass ejection. It's like a big blast of solar materials and magnetic fields that leaves the sun. And this one happened just around the corner on the sun's far side. So when did that happen?
It happened at approximately 1800 UT, which that would be that's 6 o'clock UT, which would be about 1 p.m. Eastern time or 12 p.m. Central time on the 21st. So not today, but yesterday. So yesterday afternoon, basically.
So yesterday afternoon this happened. And
Mhm.
so since it occurred on the side of the sun that's not facing in Earth's direction, let me
Mhm.
go to the next slide because um, so there's the spacecraft and there's the Earth, and you can see that the blast went out on the far side of the sun, so that blast should not be coming our way, and yet these particles did come our way. So,
Right. So what you're looking at here, this is actually not solar SOHO that I pointed out. This is solar orbiter.
yeah.
And the reason that I pointed this out was because in some of the past times we've seen these events on the far side, we actually, solar orbiter was on that side of the sun, and we were able to actually determine better what happened. But the location of solar orbiter is not too far off from where SOHO is.
Oh, okay.
Um, and the reason that we can see those particles is because of the sun's magnetic field, because it comes out in a spiral.
There it is, the
Right.
Parker spiral.
Right. So if you look at that, so the planet that we're just gonna that planet is actually Mars, but let's just pretend that's Earth, okay? Because I can
You can see some little, if you look really closely toward the center of this image, they've got some little orbits drawn in
right,
that
right.
are
So those are three, yeah, Mercury,
Mercury,
Venus, and
Venus, and
Earth.
Earth. Yeah,
Right. So let's
they're
pretend
just right in there.
that's planet on the outer side. If that was Earth, for example, if you look at that spiral that is about to that planet, if you trace it back, it actually goes back to the backside,
Yeah.
right? And so what's happening is those magnetic fields are coming out radially, okay, away from the sun, but the sun is rotating. And what that means is those magnetic fields are also curved like this. We call this the Parker spiral, or sometimes it's called the ballerina skirt. And this is actually how the solar wind comes out too, because the solar wind also comes out radially, but that's only if the sun isn't spinning, but the sun is spinning. And so what that means is these particles that are coming from the sun, protons, electrons, and even sometimes bigger particles, they're charged. Okay, they have electric charge, and that means that they follow magnetic fields. In fact, electrons and protons will spiral around magnetic fields. And so they will preferentially follow the magnetic fields that are connected to where they are. So, what that means is this magnetic field that's coming out of the sunspot region or active region actually, from the backside, curves around and
Wow.
connects with Earth. And so it's like a highway. It's like a super particle highway that they follow, and that's why we see them at Earth.
Okay. So let's talk for just a second about that particle storm. So, because
Mm-hmm.
I've heard you call that a radiation storm. Is that harmful to us?
It is not harmful to us because we are protected by our atmosphere and by the Earth's magnetic field.
Okay. And but it does have an effect on Earth, correct? So there were some
It
effects.
does. Yeah, it can have several effects. So one of the things that happens is those particles, because they are charged particles, when they get to Earth, they also tend to follow the Earth's magnetic field. And so the Earth's magnetic field is like a bar magnet. Okay, you may remember in class and science class when you put up a bar magnet and you sprinkle um, iron filings around them, you'll see the lines of the magnetic field. Okay, and they come together at the north and south pole, or the plus and minus of that bar magnet. Well, so that's what happens at the Earth's north and south pole. The magnetic fields come together. And so when these particles come in from the sun, they follow the magnetic fields. And when that happens, those particles hit the upper atmosphere. The atmosphere is protecting us, but it's disturbing the ionosphere. And what that means is that it changes the ionosphere. So certain frequencies of radio waves are no longer transmitted properly, they're absorbed. The same effect actually happens during a solar flare.
Okay, and so like on this illustration, which is showing that, what did you call it? Polar cap absorption? Is that
It's called polar cap absorption, correct?
Polar cap absorption, okay. And so that's what this illustration is showing. So let's go back. So there was a flare on the sun. It sent out these energetic particles. They moved along this particle superhighway, as you called it, in this spiral shape. They did hit the Earth, even though the event happened on the far side. And they affected, this illustration only shows the North Pole, but they affected the Earth's north and south magnetic poles. So it was the event was a magnetic event, and it came and it affected Earth's north and south magnetic poles. And this illustration is showing little airplanes. I don't know if everybody can see those, but there's some little airplanes on here that are going, taking kind of a zigzag line. So when this kind of event happens, do people at NOAA's space weather forecasting, do they get on the phone with the airplane folks and say, hey, this event happened? And so what would happen to those airplanes if they didn't do that?
Well, there's a couple of things that'll happen. The most important aspect is the communication. So communications in certain frequencies is disrupted, primarily high frequency, or what we call, so high frequency radio waves are disrupted. And so this is of importance for aircraft, because they need to always be in contact with the ground. They need to always be in contact with various airports, and if they're traveling over the poles, which is what you do when you want to take a trip from, let's say, New York to Singapore, or New York to China. You typically go over the poles because that's a shorter trip. But airlines will then have to redirect their flights if that happens, because they may lose communication. And that's something that they don't want to happen, because it costs them more money. It costs them more fuel to do that. But in addition, if these radiation storms are strong enough, now this one was probably not that strong, but if they're strong enough, that radiation can penetrate some into the upper atmosphere, which can be detected or picked up by aircraft. So as a pilot, or if you are an airline attendant, if you take that route a lot and there are a lot of these radiation storms, you would have a overall higher dosage of radiation.
Right, because the radiation is cumulative, right?
Exactly. Yeah, exactly.
Yeah, so I learned that from watching the series For All Mankind on Apple TV, which was a very good series. But the amount of radiation that you get, space radiation that you get, it accumulates. And over your lifetime, you only want to get up to a certain level. So
that actually is important here, because these radiation storms are of concern for astronauts, because they're not protected by the atmosphere, and they're not protected fully by the magnetic field, because they are much farther away from the surface of the Earth.
And I read something else that was saying, if you're in aircraft and you're flying over the poles and one of these radiation storms strikes and it knocks out your communications, and at the same time you're trying to go lower or change your route slightly to account for that, you don't know about these other airplanes that are out there also flying over the poles, that are also changing their routes, that are also out of communication with the,
Right,
so it sets up a potentially dangerous situation for aircraft. And yet
right.
what can we do? Because these events happen in a matter of like, how long does it take this radiation to get from the sun to the
It
earth? Is it
it
travel at the speed
takes
of light?
it doesn't travel at the speed of light. It's slightly slower. It's close to the speed of light, but the speed of light from the sun is 8 minutes. These
Right.
particles take more like somewhere between 15 to 20 minutes. Because also remember, they're not traveling directly. They're
Oh,
following the
right.
magnetic
Yes.
field of the sun.
Right.
So we do sometimes have a warning. Um, and that would be something that NOAA will monitor. These radiation, in fact, the scale for what we call a radiation storm, the scale of 1 to 5. There's a S1 to 5. This was up to an S2, and that just is determined by how strong it is. Um, and so right now, NOAA would have alerted the airlines, but more than likely, it looks like from looking at the data that this particular event actually had a stronger impact on the South Pole than the North Pole.
Less air traffic over the South Pole, so
Exactly, exactly. So it's
yeah,
not as big of a concern.
right. Okay. So, I mean, it seems like we don't get these all that often, like maybe once a month, every 6 weeks, every
We
couple of
don't.
months?
Yeah, they're comparatively rare. I mean, we get CMEs and flares regularly, even during
Right.
solar maximum, but we don't see these particle events regularly. And part of the reason is it is more dependent upon where the particle event occurs.
Right.
So there may
Okay.
be more particle events that are happening, but we don't see them because it may not have been magnetically connected. We call it well connected. We say magnetically well connected, meaning that a magnetic field that those particles are traveling on actually passes Earth or a spacecraft. We do sometimes see them from spacecraft, and we don't see them at Earth because the spacecraft is at a different location and the magnetic field is actually connected to that spacecraft.
I see. Okay. So let's move on because we've got a bunch of other things to cover here. I just want to flip through. So, this was one of the events that happened this week. It just happened
Mm-hmm.
yesterday, this solar flare and solar radiation storm that came and struck Earth's north and south poles and caused a radio blackout over the North Pole, but may have been stronger at the South Pole. But we also had some other events on the sun this week. We had this is actually from the 20th, this
Mm-hmm.
M flare, and this is that same sunspot region I think that you mentioned that
Exactly.
rotated out of view.
Exactly.
Right,
Now, in this case, it still is somewhat out of view. So this is actually one of the things that's interesting. Oftentimes, flares uh, they're typically happening. Well, they are happening in the magnetic loops high up in the solar corona. So you can imagine that sometimes those, even when that sunspot region rotates around, those loops can still be seen from our vantage point. And that
right.
means that these flares will still be seen, but only partially, because that means that the bottoms of those magnetic fields, we call those the foot points, where the magnetic fields connect back to the sun. We can't see that, and there some of the flare energy happens there. So we don't see the full flare. The flare is actually partially blocked, or we say occulted, by the sun itself. And
And
that
so
means that the flare may be bigger than what we see.
oh, right. So this was an M 1.2 flare, which was not a hugely strong M flare. It was a very
Hmm.
moderate flare, but it may actually have been stronger because we couldn't see the whole thing.
Exactly. Exactly.
Right. So, and this guy, this sunspot region was very active when it was on the Earth facing side, but the sun is rotating, turning here to the west and carrying this spot out of view. So now it's gone, but we've got some other sunspots. I should have put in I'm going to start doing that. I'm going to start putting in today's sunspots because I noticed today there were just a bunch of spots on the sun. I just want to show a couple of pretty pictures before I take a break. But this one is the just a prominence that came
Hmm.
off the sun on the eastern side. So this one is a region that's rotating into view, right, Alex?
Correct.
And I think this one is one going out of view as well. I'm not sure if that's that same one, but it's a very,
No, that's a different one. Yeah, that is a different one.
yeah,
And in fact,
beautiful.
this particular time, there was one looping out like that on the west side and another one looping out on the east side
Oh,
at the
cool.
same time. So the sun had these little legs coming from the bottom.
Awesome. Well, I love to show these because it's just like, I mean, I look at these every day and I never get tired of looking at these. It's our star and we love it. It's very
It's
beautiful.
amazing. It's
It's
amazing. And it just
amazing.
always has something interesting to show. And every time, what you're seeing is unique. Every single
It
event
is.
is different.
It is. And speaking of something very interesting, take a break here and just tell you that the EarthSky lunar calendar, also very interesting, is available now. The calendars have come in. In fact, I just saw an image that I almost put in with a huge stack of calendars all rolled up in their tubes and ready to be mailed off to people who have already ordered calendars. So these calendars make the best gifts. And there might be some people here in this live stream who might give some gifts of calendars this year.
That's right.
Maybe, maybe.
Maybe.
And but we won't tell. And these calendars are great. So if you guys would like to order a lunar calendar, come to EarthSky and come to this link, earthskystore.org, and check out those calendars because it really helps us keep going and gives you a very cool holiday gift, New Year's gift, or holiday gift to give to someone that'll make them think you are like the coolest person ever.
They
Because
are
I know
cool. They're very cool.
they are, they're really cool. Okay, so before we go, let's talk about solar cycle 25. I mean, we have talked about this. We've been talking about it, but what's the story, Alex? We peak? Do you think we peaked in
Yeah,
October?
so this is exciting. So I will say one of the things that I'd like to do on a future cast, maybe after we come back after Thanksgiving and take a break, is
Okay.
actually talk a little bit about some of the more details, like how many flares do we have, how many CMEs do we have, and how did that change over time. But right now, you can see here we're looking at the sunspot cycle 25, which is the current one we're in, and what we see here is that August so far had the highest monthly average, monthly value. Take all of the days, add them up, and divide by the number of days. That gives you the average. So the monthly value for August was 215. And we can see now that October, we still are in November, so we don't have the full numbers for that yet, dropped significantly. So the question is then, is that peak in August? Is that the peak? Have we reached the highest point? Um, and maybe, but we don't know yet. Um, Now, there's a good chance that we might have because the solar cycle, the maximum part, is actually not one period. It's actually a period of 1 to 3 years. Okay, and we
Right.
think that we might have reached the middle of that, and we're kind of going towards the end of that now. Um, but we have to wait for a few more months to see if this is in fact the case. Now you can see that the prediction, which is the red curve, we're a little bit above it, but we're kind of sort of following that trend. But one thing you might notice is, and you can notice this if you go back and look at previous solar cycles, sometimes there's two peaks.
Right.
And it is looking like what we're going to have here are two peaks, maybe.
And why are there two peaks?
Well, the reason that there are two peaks is because the hemispheres, the northern hemisphere and the southern hemisphere, are active at different times, and so they're out of sync. The northern hemisphere has already reached its peak. As a matter of fact, I remember you showed maybe last week or the week before, you showed that really cool image that somebody had made, which was combining all of the sunspots over a week. And you'll notice that the strip on the bottom was much denser than the top. So the southern hemisphere had more sunspots than the northern hemisphere. And that
was just for October.
Right. That was just for October. So what that's saying is October, you were seeing most of the activity coming from the southern hemisphere. And that was in fact the case for August. What we believe is that the northern hemisphere has already peaked closer to the beginning of 2024. And so that may be the first peak. And then the second peak would be the peak for the southern hemisphere.
Right. But my understanding is that we can expect high activity on the sun for maybe another year.
Right. So that's the thing is, the other thing to notice is that you can still have big events even when, these are sunspot averages over the whole month. So that doesn't mean that we don't have, periods during a month, even when there's less overall activity, that are very high. So we may still have, a week of high activity, then maybe not a week of low activity and low sunspots. So the average might be not as high as, let's say, August, but we could still see some pretty substantial activity, and we will more than likely we will see some more activity.
Yes. So if you haven't gotten on that plane and gone to Iceland yet to see auroras,
That's
still
right.
time.
That's right. Well, yeah, you're going to still have at least a year, maybe 2 years to go to Scandinavia or to go to Fairbanks, Alaska, something like that. And I'm going to be going to Iceland and to Finland over the next two years. So I'm looking forward to it.
Oh, good for you. I'm so glad you're doing that. Well, I just have one more slide to share, and I ran into this morning, and you told me you could explain this because I have no clue what this is about. So what is this?
Well, let's see here. So what you're looking at, a couple of, so there actually have 3 cycles here. You see cycle 23, cycle 24. Part of what you'll notice is these little red areas start at higher latitudes. Okay, that's where sunspots are starting at the beginning of a solar cycle. So one of the things that happens is the sunspots start at a higher latitude, and over the solar cycle they move to a lower and lower latitude. So you see they're coming together, kind of converging at this point. Okay, so that's part of what you're seeing there. Let me.
Oh, wait. I suddenly get it. So up in the upper right, I'm seeing, I bet the people who are watching can't really notice this because it's so tiny, but I can see it on my screen. There's a tiny little 26 up there in the upper right. And I think what that's about is they think that solar cycle 26 has already started because they're seeing this activity.
Right. That's exactly it. So
yeah,
because
okay. I get it.
So notice this. Okay. So sunspot cycle 23 ends. Okay. at about 2008 or 9, okay?
Right.
But cycle 24 started before that. So that is what this
Oh,
is
yeah.
showing. And this is a really big deal that these cycles, they overlap. And there's another way that you can see this. So if you watch sunspots and you look at their magnetic fields, what you will notice is that when you have a sunspot group, they tend to be slightly shifted as they move across the sun. And so at the front, they'll have one polarity, positive or negative. But at the back, they'll have the opposite polarity. Okay. But when you go to the southern hemisphere, it's switched. And what we're noticing, and
Like,
so all the sunspots will be of those particular polarities, okay? And so as they move across the sun for the whole solar cycle, that's what you normally see. But what we do start to see is we start to see sunspots that pop up in a particular hemisphere that are backwards, okay? And that may be the indication that these are sunspots from the new cycle.
oh, wow. That's so
So you can
cool.
see that. Yes, you can see that. It is really, really cool. So it does happen, and it happens every so often. You'll see a sunspot that's the wrong polarity for that cycle, but these could be sunspots from the new cycle coming up.
That is super awesome. So even as we're sitting here saying, have we reached the peak of solar cycle 25? We seem to already be seeing the beginnings of solar cycle 26.
Right, right. Now, what we're looking at here, this data is not sunspot. This
Oh,
data is actually looking at oscillations in the sun, specific type of oscillations. So this is helioseismology.
oh, okay. This isn't
Yeah.
sunspots. Okay.
So this is not sunspots. Let me clarify. This is not sunspots. Now, what I wanted to point out is that sunspots have that same kind of pattern. Okay, they start high, go low. Okay, but what you're seeing is particular frequencies that are measured via helioseismology, and they're due to specific kind of oscillations. I won't go into the detail right now because
So like
there's a lot
waves
there.
inside the
Yes,
sun, kind
because
of
the
similar to
sun,
seismic waves.
right, but the sun vibrates on its own. Okay, all the stuff that's happening inside it vibrates, and it vibrates at lots of different frequencies. Um, and we can measure the changes in the light on the surface, and we can figure out what those frequencies are. And those frequencies tell us all kinds of information. They allow us to see inside the sun and see rotations and patterns. In fact, they allow us, when there's a very strong sunspot on the far side, we can often see that through using these oscillations. It's like, we can use these waves, these sound waves, to see stuff on the other side. And we do that regularly, which gives us an idea of, hey, there's a really big sunspot that's going to be rotating into our view soon, because we can see it using helioseismology.
Okay, I have a question.
Mhm.
So on the Earth, seismic waves happen when there are earthquakes. Are
Right.
these waves that you're talking about, these vibrations inside the sun, are they happening like continuously?
They're happening continuously.
And
Yes.
so
The sun
is
itself
it like the sun
is.
is doing like an earthquake at all times?
Yeah, yeah. Now we do actually see things we call sunquakes. Those happen during a solar flare. So sometimes when there's a big solar flare, that sends energy downward, and that creates these huge ripples. It looks just like ripples in a pond, and we call those sunquakes. Those happen specifically usually with some sort of eruption. But the sun, you can think of, if you blow a bubble, okay, you've got a bubble pipe and you're blowing bubbles. You can see those bubbles when they're moving. They're doing like this. Well, the sun, it's not a solid body, and it's also rotating, and that means that things are wiggling inside of it. And so It's wiggling with lots of different frequencies, depending on what's rotating, depending on what's in there. And we can look at those different frequencies and we can work backwards and figure out what's happening.
Yeah, see, you're all excited about figuring out what's happening. I'm just still back here at the fact that it is happening at all. It's like, wow, like the sun is doing this thing all the time. Like that's so wild.
Well, we've released. As a matter of fact, I did a podcast one time called "Sounds of the Sun." You could probably like Google "Sounds of the Sun" Soho. I did it. NPR picked it up, and so I talk about this, and you can hear the sounds when they actually took the vibrations. Now the vibrations were far too low for us to hear with our own ears, the particular frequencies, but they just use what's called audification to put it into a range we can hear. But I've heard somewhere somebody say, if those sound waves from the sun could actually travel through space, fortunately they can't because there's no air in space. But if they could, the sun would be deafening.
Yeah, we'd all be like, ah!
Yeah, it would be really, really loud.
Right. Wow. Okay. Alex, thank you. That was super interesting. So, wow, I'm going to be thinking about that one. So we have two things now that we're going to be looking for. And one is we want to see those images that people captured during total solar eclipses of coronal mass ejections. We're looking for those.
Right.
And I want to hear those sounds from the sun. So hopefully we can get one or both of those things for next time. And that's all we've got for today. We will not be here next week on the Friday after Thanksgiving, but we'll be back in 2 weeks with more sun news.
And we'll have lots to talk about.
You'll have lots to talk about. And Alex, thank you so much. I really appreciate it. This was so interesting. And I hope everyone enjoyed it as much as I did.
I hope so too. This was a lot of fun.
It was.
As always.
Yeah, thank you, Alex. One Earth, one sky.